Welcome back. It's time for another lesson. We're going to be working this week on something completely different. No more integrating ordinary differential equations. We're moving on to Monte Carlo methods, and the technique I want to focus on this week is called the Demon algorithm. And why would we be interested in such an algorithm? Well, the idea is we're trying to do thermodynamics, and one of the interesting things about doing thermodynamics is studying equilibrium. So in order to reach equilibrium, a system needs some mechanism for exchanging energy between its various components. And so the Demon algorithm is really just sort of a bookkeeping trick for managing the exchange of energy between pieces of a system in a way that conserves energy in the long run, but doesn't necessarily conserve energy in the system in the short run. Basically what happens is the Demon is sort of like a little tiny system that can be given or can provide energy to the system in order to facilitate the exchange of energy between pieces. So the idea is you set up the rules for modifying the energy in the system in such a way that the energy remains conserved in the long run. The Demon gets a little, it gives a little, but it doesn't allow the thing to go arbitrarily far in any particular direction. We'll see how this works in a minute. But the idea is, if you let it go for a long time, eventually the energy will distribute itself in a way that's very likely. So from 153, you guys may remember that there's this concept of entropy. And if you just let the system sit for a long time and energy is allowed to move around, it will ultimately find itself in a state of very high entropy. And so the Demon, one way to look at it is the Demon is just a way to move energy around in the system so that energy is conserved, but that enables the system to discover sort of on its own through statistical fluctuations the state of maximum entropy. So let's talk about the algorithm itself. How does it work? So you have a system that has many pieces, and each piece can have a certain fraction of the total energy, say, and then you imagine you have a Demon, and what you do is you make a small change to the system, and then you check, is that change physically possible? So for example, the demo that I'm going to show you in a moment, we're going to be talking about molecules that are able to move up and down vertically, but there's a floor, so they're not allowed to go below the floor. There's something in the way. They can't just keep going down, down, down. They have to stay above a certain minimum height, but other than that, they're free to move however they like. Their energy, of course, is going to go up the higher they go because of the gravitational potential energy, but they're not allowed to go below zero. So then the other thing you check after you make your small change, as long as it's physically possible to make the change, then you calculate the change in the energy. Basically, if the change in the energy is negative, you take it no matter what. If the change in the energy is positive, then you have to verify that the Demon has that much energy. If the Demon has that much energy, then you take it from the Demon and you put it in the system. If the system loses energy, you give it to the Demon. So the Demon is the repository of energy in cases where the energy goes down due to your small change. And it's the source of energy that enables the change to actually occur if the energy goes up. But if the energy goes up so much due to your small change that the Demon doesn't have that much energy, then you simply reject that change and say that change is not possible because my Demon doesn't have enough energy to do it. And that's the way in which you enforce energy conservation. The Demon is like a small extra degree of freedom that's not really part of the system, but it exchanges energy with the system. And we're going to see in a moment that in that sense, the Demon represents a sort of ideal mini thermometer that you can use to measure the temperature of the system. So that's the way it works. Let's look at the demo and see how this thing really works in practice. Okay, so here we are looking at the Python notebook that I posted on the ACE site that you guys could use. And here is the Demon algorithm, yet again, explained. And I want to talk about our example problem. So what we're going to be looking at is a collection of nitrogen molecules near the Earth's surface, and we're going to assume that the temperature is some constant value. The system has a definite total amount of energy, which we basically determine by creating the system with a distribution of altitude. So these nitrogen molecules are going to start out with a distribution of heights, and if you add up the potential energy of all the molecules, that's the total energy in the system at the beginning. Because the Demon algorithm conserves energy in the long run, that's going to be the total energy in the system at the end as well, except for a possible tiny amount of energy in the Demon itself. And point is, we're going to completely ignore any energy associated with the motion of the molecules. So the only thing we're going to get is a distribution of heights. So if we're interested in the density of molecules as a function of altitude, this is the way you would do it. Now, if you were interested in the velocity distribution, you'd have to keep track of the speed of the molecules, for example, or the x, y, and z components of velocity if you wanted a three-dimensional velocity distribution. The program I want you guys to write is similar to this one, except instead of keeping track of the altitudes of the nitrogen atoms, I want you to keep track of the x component of velocity. So you're just going to go in and bump the x component of velocity of one molecule randomly, and then calculate the change in the energy of the system due to that, and then use the Demon algorithm to keep track of all that energy. And ultimately what you'll get is a distribution of x components of velocity. But let's go ahead and look at this. So the potential energy of a molecule at a height y above the surface is just mgy. I'm also assuming that the altitude doesn't change enough that we need to worry about the universal law of gravitation. We'll just assume the gravitational force is constant. That, we could argue about whether that's a reasonable assumption or not, but that's the assumption I made in the demo. And so we fire up the PyLab interface. I set the mass of a molecule equal to 28 AMUs. I've got G as 9.8 meters per second squared. I've got the Boltzmann constant. And then we start the Demon out with no energy. I'm going to start with 10,000 molecules, and I want to iterate for 400,000 times. And the height scale we're going to be using, this simply determines the range of heights over which the molecules is originally distributed, and it also sets the scale for the change in altitude that I make each time I update the position. Every time I go in and bump a molecule around, I'm going to need a height scale to determine the distribution of sizes of bumps that I make. And so that's what H does. It doesn't actually show up explicitly in the data. It just gives me an order of magnitude of energy and height change, basically. Now, originally, I'm going to call the setup function. I create the setup function. You pass in the number of molecules you want to use, and you pass in a scale, a height scale, and it distributes the molecules uniformly over, it uses a uniform random number to distribute the molecules randomly between 0 and L, whatever L happens to be. So that's sort of how that works. And then this is the main guts of the algorithm. I called it shake because basically what it does is it goes in and moves one thing. It's kind of like shake the thing up a little bit. You pass in the array of y's, the array of altitudes. You pass in the current value of the Demon energy, and you pass in the amount by which you would like the scale over which you would like the y value of a particular molecule to change. We'll see how that works in a moment. First of all, we need to randomly pick a molecule out of our array. So I take the length of the array, I multiply by a random number between 0 and 1, and then I truncate that as an integer. So I take the int of a random number between 0 and the length of the array, and I get an index. Then I calculate the change in y as a normally distributed number with a variance of 1 multiplied by delta. Remember, delta is my scale, so I'm going to have to pass in something for delta that makes sense for this problem. But that's basically how it works. Then I calculate the change in the energy. In this case, it's delta y times the weight. If I start out saying that I don't accept it, but then if the change in energy is less than the Demon energy, and the change is physically reasonable, okay, then I decrement the Demon energy by the change in energy. I update the y value of the particular molecule by the change in y, and I set accept equal to true. So all those things happen if I've decided to accept the change. Otherwise, I don't change the Demon energy, and I return accept as false. So the return value for this function shake is the new Demon energy and whether or not I accepted the Demon energy, accepted the change to the Demon energy. Notice that the array is not returned as part of the return because I've already gone in and changed the array. So it's already been monkeyed with. There's no point in returning it because it's already changed. Okay, so here's the way the thing works. I call setup. I pass in n. Remember we set that to 10,000. I set L equal to h. That means I'm going to distribute these altitudes randomly between 0 and h. H was 20,000 meters. So I have an approximately uniform distribution of molecules between 0 and 20,000 meters. That gives us sort of a sense of what the energy is likely to be. Now notice that doesn't fix the energy. If I wanted to give the energy a definite value, I probably should set the molecules up at definite heights rather than randomly distributing them. But this gives us an idea of what the energy should be like. And then I just iterate over and over again. I call the shake method. I reset the Demon energy and check the value of accept. Now one thing I'm doing here is I've got a Demon list, I call it, and basically it's just a list of all the different Demon energies that we visit as we shake these guys up, and I'm adding the new Demon energy onto that list every time. So when I'm done, I should have a Demon list that has M entries. In this case, that's 400,000 entries. So it's going to be quite a long Demon list. And if I accept the change, I'm going to increment the accept count. So accept count tells me how many times did I accept the change. And then I make a graph here of the distribution of heights at the end. And notice I'm using a new function here. This is sort of like the plot function, but it generates a histogram. So I use the hist function to generate a histogram, and I tell it I want 40 bins. I think the default number of bins is 10. So if you want more than 10 bins, you need to specify the number of bins. You can also specify the bin edges, but I'll let you look into that. That actually does remind me. One of the things I occasionally gotten questions about a function. What does this function do? So if you ever wonder about a function, let me just point out that you can just type the function name and then hit tab, and the interface, let's see if I can get this to, yeah, the interface comes up with all kinds of help. So you can go in and get help about any function you like by just starting to type the function in. Let's see if I can close this thing. Now it won't close. That's beautiful. Okay, well, that's lovely. I don't know why it's not closing. It's something with my browser, I guess. Let me just get it out of the way that way. So you can just type the function in and hit tab, and it should give you help. Hopefully it won't be quite as annoying as not go away when you say it's time to go away. But anyway, I'm also printing out the accept count divided by m. That's the percent of accepted energies. And you want this to be fairly high, like 60 or at least 50% or more. Otherwise, you're doing a lot of work and not accepting very many of the changes. You'll notice in this particular example, it was accepting 77%. If the percent accepted goes too low, what you want to do is go back in, and when you call shake, call it with a smaller delta, because if your delta is too big, you're not going to ever accept, or rarely accept, I guess. Okay, so let's see. And this tells you the average height. I calculated the average height by taking the sum of all the y's and dividing by the length of the y array. So you can see that average height ended up being something like 10,000 meters. So, and there you have, there is the exponential. This is obviously some kind of a roughly exponential distribution, and you can see that the altitude, I mean the number of nitrogen molecules drops off as you go to higher and higher altitudes, and that sort of makes sense. So now let's look at the Demon energies. It turns out remember we did 400,000 Demon energies because I iterated 400,000 times. You can see that this is also roughly exponential, but the energy range is quite small because these are nitrogen molecules. They don't have that much potential energy because there's so little mass. But what we're interested in is seeing if we can extract from this distribution of Demon energies the temperature. And the idea here is that the Demon acts like a small system connected to a reservoir. The reservoir is the system we're actually interested in, these nitrogen molecules. But as a small system connected to a reservoir, it should have a distribution of energies that obey the Maxwell-Boltzmann distribution. And so we should be able to get the temperature by fitting the number of times the Demon visited a particular energy versus an exponential, or the log of the number of times the Demon visited certain energies versus the energy. And that should be, if you take the log of this expression, you see it should be a straight line with the slope equal to minus 1 over kBt. So the idea is there's in SciPy.optimize, there's a function called curve fit. It's a lovely function. You pass in, I'll show you how it works here. You pass in a function, the x values, the y values, initial guess at the parameters, and you pass in an estimate of the error. Let's see if I can get this to show up in the screen. There you go. You pass in an array that gives you the uncertainty in each of the values. Of course, these values are counts, and so the uncertainty in the log of the values should be 1 over the square root of the number at each count. So that's kind of the idea. The uncertainty in the count is the square root of the count. The uncertainty in the log of the count is the uncertainty in the count divided by the count. It's like dx over x is the derivative of log x. And so that turns out to be 1 over the square root of the number in each count. And if you put that all in, you can look at the code in the demo to see how to set it up. But basically, you pull out, once the curve fit runs, it passes back the optimal parameters, and it passes back this thing called the covariance matrix, which is a n by n matrix, where n is the number of parameters. And the diagonal elements of that give you the variance of that particular parameter. So you can take the square root of the variance and calculate the uncertainty in the parameter. So what that boils down to is we're doing a linear fit, so we have a slope and an intercept. Notice the function here, f linear, has a slope and an intercept. So we have a slope, we have an uncertainty in the slope, we have an intercept and an uncertainty in the intercept. And the temperature is going to be minus 1 over the slope times the Boltzmann constant. So we go ahead and put all that in, and we make a graph. And you can see, let's see, I think you can see, yep, here we go. There's the graph of the log of the number of Demon visits to a particular energy versus the energy. And it's a nice straight line. It gets a little dicey at the end because the counts get fairly low at higher energies, but the fit turns out very nicely, and we get a temperature of 300 Kelvin, more or less. And that's sort of consistent with the numbers we put in. So that's the idea. What I want you guys to do for Project 5 is to basically do the same kind of thing, but this time, instead of looking at the distribution of heights, I want you to look at the distribution of x component of velocity. So you're just going to change the bump function not to bump the altitude of the nitrogen molecule, but to bump the velocity. So you're going to need to think about, how do I start the thing off? What velocity distribution should I pick to begin with? And then let the thing approach equilibrium, and take a look at the velocity distribution and the temperature that you end up with. And that's all there is to it. We'll talk to you guys next time.